We have discussed how we can perform principal component analysis to achieve dimensionality reduction. Well, it turns out there's a very close relationship between principal component analysis and a technique we discussed earlier in the context of structure from motion, which is singular value decomposition. So let's talk about that. So first, let's recap what we did in the context of principal component analysis. So we first construct our data matrix F, which is just a stacking of all our images, F1 through Fm as columns. That's an n by m matrix. And then we can compute a covariance matrix R, which is F transpose. That's an n by n matrix. And as we said before, we can solve the eigenvalue problem R E equal to lambda E. That gives us all the eigenvalues and eigenvectors of the covariance matrix R. And we are going to choose, using some method, the first k of these eigenvectors, and those are the principal components, and that gives us an orthonormal basis in which we are going to represent our image set, also known as a linear subspace, also known as the eigenspace. So that's PCA. Now, let's talk about a method we have talked about earlier, singular value decomposition, a very powerful technique, very widely used, like PCA in linear algebra in many different domains. So what is SVD, singular value decomposition? What we showed before is that for any matrix A, there exists a factorization. You can take A, which is, let's say, an n by m matrix, and factorize it into U, sigma, and V transpose. U is an n by n matrix, V is an m by m matrix, and sigma is an n by m matrix. Now, these are not just any arbitrary matrices. That's what makes SVD very powerful. They have special properties. These are special matrices in the sense that U and V are orthonormal matrices, very much like rotation matrices we have talked about before. Orthonormal matrices, so that's special. In addition, sigma is a diagonal matrix. It's a diagonal matrix, and its diagonal elements are called the singular values, and that's why we call it singular value decomposition. In fact, these are non-negative numbers, so it's called a positive semi-definite matrix. It's a non-negative numbers, and they are ordered in descending order of magnitude. So sigma 1 is the largest value, then sigma 2, and so on. And the number of non-zero sigmas we end up here in sigma has to do with the rank of the matrix, which we discussed earlier. So these are the singular values. And so that is what singular value decomposition gives you. Now let's apply singular value decomposition to our data matrix F. So we have a data matrix F, which is just another matrix. F is an n by m matrix, and it can be factorized into a U, sigma, and V. And now we can construct our covariance matrix R, which is F transpose. F we know is this, and F transpose is the transpose of this. So we say U, sigma, V transpose, that's F, and then V, sigma transpose, U transpose is F transpose. And now take a look at this right here. Your V transpose V, we know that V is an orthonormal matrix. So the transpose of an orthonormal matrix is the inverse of the matrix, and therefore V transpose V is the identity matrix. That just goes away. And you can rewrite this expression as U times a new matrix lambda times U transpose right here. And what is lambda? Lambda is just sigma times sigma transpose. So it's a diagonal matrix, which is multiplied by the transpose of the diagonal matrix, which is a diagonal matrix. And so lambda looks like this. Lambda is an n by n matrix, and it remains a diagonal matrix where the diagonal elements are now lambda, small lambda now, and each small lambda I is just the singular value of f, if you remember, sigma I squared. So that's it. And these are again non-negative numbers, and they are in descending order of magnitude, once again, just like the singular values. And in fact, these are exactly the eigenvalues of the covariance matrix that we are looking for. Furthermore, if you look at the matrix U, U is constructed of all the eigenvectors corresponding to the eigenvalues right here. And the eigenvectors, as you know, are the principal components that we are looking for. We can have n eigenvectors and n eigenvalues here. We may choose to use fewer of them, and that's our plan, but indeed we can have n eigenvectors in here. So that's the relationship between PCA and SVD.